Hello everyone and welcome to another lecture of Machine Learning Foundations. We will continue with what we started this week and give a brief recap of univariate calculus and the concepts that are required for the rest of the course. Once again, most of these are concepts that you would have seen in Math 1 or Math 2, but these deserve repeating. Here is a brief overview of this module, which is we will give a brief recap of continuity and differentiability. When is a function? Now this entire chapter we are going to have functions, real valued one dimensional functions. F is from R to R. When can we will say F is from R to R is continuous at a point x star in R if for all sequences converging to x star, all sequences x1, x2 dot 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 converging to x star, we have that f of xi converges to f of x star. What does it mean by that? We mean x limit I approaching infinity xi equal to x star implies limit I approaching infinity f of xi equal to f of x star. Or you will write this as more compactly, limit x approaching x star f of x is equal to f of x star. So this is the statement for a function f being continuous at a given point x star. Here is one first example here. Let us have example 1 as sorry, let us say we have first example here as f of x is equal to x squared. We want to test whether this function f is continuous at x star is equal to 2. Let us say, what does it mean to say that this function f is continuous at x star is equal to 2? It means that give me any sequence that converges to 2, any sequence, the f of that sequence should converge to f of 2. What do I mean by that? Let us say an example sequence that converges to 2 might be, let us say 3, 2.5, 2.25, dot dot dot. This clearly converges to 2. This is the xi sequence. What about the f of xi? Well, f of xi is 9, 6.25, 2.25 squared is, I do not know what exactly that is. So 2.25 squared dot dot dot, it will, now you have this sequence f of xi. You can clearly show that as your xi approaches 2, f of xi will approach f of 2, which is equal to 4. So this will approach 2 and this will approach 4. So we have that f of x is equal to x squared is continuous at x star is equal to 2. In fact, it is continuous at everywhere, but this particular argument only says that f of x is continuous at x equal to 2. Here is one more example. Let us say example 2, f of x is equal to sine of x. By that we mean this thing, f of x is equal to minus 1 if x is less than 0, equal to 0 if x is equal to 0, plus 1 if x is greater than 0. This particular function is an example of a function which is not continuous at the point x star is equal to 0. Let us say x star is equal to 0. Now I will give you two sequences, both of which converge to 0. Right. Consider the sequence 1 comma half comma 1 by 4 comma dot dot dot. This is a sequence xi. Right. What is f of xi? F of xi is f of 1 is equal to 1, f of half is equal to 1, f of 1 by 4 is equal to 1, and so on. So, this is a sequence consisting of just 1s. So, clearly this sequence converges to 1. The first sequence converges to 0, xi sequence converges to 0, f of xi converges to 1. But this is just one sequence, right. So, we can have one other sequence which converges to 0. For example, let us say pick xi as minus 1, minus half, minus 1 by 4, so on. This also converges to 0, but f of xi does not converge to 0, but rather it actually converges to minus 1, because every element for every element in this second sequence here, we have f of xi is actually equal to minus 1. So, we have just infinite number of minus 1s, which means that this f of xi sequence converges to minus 1. So, this clearly violates the statement here, right. So, we have for all sequences converging to x star, we must have that f of xi converges to f of x star. So, f of x star in this particular case is actually equal to 0. So, we have one sequence converging to 0, but f of that sequence does not converge to 0, and similarly you have another sequence converging to 0 and f of that sequence converging to minus 1. Right. So, in fact this is not the property of just defining f of 0 equal to 0. If we had defined f of 0 to be anything, f of 0 to be let us say plus 1, even if we had defined it to plus 1, it would the first sequence does seem to satisfy that. Right. You have xi converging to 0, f of xi converges to 1. It does seem to satisfy the definition of continuity, but it would violate the definition of continuity for the second sequence. You can have a second sequence which also converges to 0, but f of xi converges to minus 1, which is not equal to f of 0. So, this is an example of a discontinuous function. There is a discontinuity at x star is equal to 0. Right. And we will say that a function is continuous if it is continuous at all points in its domain. Right. So, we will say a function is continuous at a given point x star if this statement is true. We will say a function as a whole is continuous if it is continuous at all points in its domain. An example would be f of x equal to x squared. F of x equal to x squared, this function is continuous at all points in its domain, not just x star is equal to 2. So, this is an example of a continuous function, and this f of x equal to sin of x is an example of a discontinuous function. Even though it is discontinuous at just one point, it is still considered a discontinuous function. Now, we will have some examples, some more examples. Let us consider this function. Example 3 as f of x is equal to 2x plus 1 if x is greater than 1 and equal to 3 if x is less than or equal to 1. This is also a valid function from R to R, and we can show that this function is in fact continuous. We have one more example. So, this is an example of this is simply f of x equal to 1 by x, and this is not a continuous function. Why is that? Because f of 0 is not defined. In fact, f of 0 whatever you define, I mean you can't define it as infinity because infinity is not a valid real number. Whatever be the value of f of 0 that you define, you can see that you can't give a valid say limit. For example, you can consider the sequence xi, this sequence 1 half 1 by 4 dot dot dot. This sequence converges to 0. What about f of xi? Well, f of xi is 1, 2, 4, 8 and so on. This sequence clearly does not converge to anything. Even though you have your xi converging to 0, your f of xi does not converge to anything. So, f of x equal to 1 by x is not continuous throughout the entire real line. But sometimes you can say that f of x equal to 1 by x is continuous if you restrict the input to be greater than 0. You can say f of x equal to 1 by x is continuous, let us say in the range, in the closed interval 1 comma 7, it is closed, it is continuous there. But the moment your domain of f includes 0, this particular function is not continuous. One other example would be f of x is equal to sine of 1 by x. This is also an example of a discontinuous function. Why is that? Because you can take exactly the same sequence as before. You can take xi as the sequence 1 comma half comma 1 by 4 dot dot dot, and what is f of xi? F of xi is equal to sine of 1. The sine is not the SIGN but rather sine cosine. Maybe I think it is better to have cosine if cosine is easier. You have this sequence 1 by 2, 1 by 4 which clearly converges to 0. F of xi is cos 1, cos 2, cos 4, cos 8 and so on. This sequence also clearly does not converge to anything, and hence this is another example of a discontinuous function. Right. So now we move on to another property of functions, which is differentiability. Right. A function f which is analogous to, which is similar to continuity, the definition would look similar. A function f from R to R is differentiable at a point x star in reals if limit x approaching x star f of x minus f of x star by x minus x star exists. When we say limit exists, which means that it converges to something, and if it does exist, that particular limit is called the derivative of f at x star, which is denoted by f dash of x star. If it does exist, if it does not exist, then you can't say anything, but if this limit does exist, then it is equal to f dash of x star. One immediate statement that you can make is, if a function f is not continuous at x star, it is not differentiable also. F is not continuous at x star, this immediately implies that f is also not differentiable at x star, but it is not the other way around. You can have a function which is not differentiable but still continuous. Here is the standard example for such a function. F of x is equal to the absolute value of x. So, it is from real to real. Here is the argument to show that this is not differentiable at x star is equal to 0. So, I will give two sequences xi is 1 comma half comma 1 by 4 dot dot dot. This sequence converges to 0. What can you say about f of xi minus f of 0 by xi minus 0, which is simply xi. What is this sequence? We can see that this sequence 1 minus 0 by 1, which is 1, half minus 0 by half is 1, 1 by 4 minus 0 by 1 by 4 is 1, and so on. Right. So, f of xi minus f of 0 xi is equal to 1. So, this sequence clearly converges to 1, this converges to 0. Right. Let us have another sequence where xi is simply minus 1 minus half minus 1 by 4 and so on. This sequence also converges to 0. But what can you say about f of xi minus f of 0 by xi? It is going to be minus 1 minus 0, sorry, f of minus 1 minus f of 0 by minus 1, but f of minus 1 is also equal to 1. So 1 minus 0 by minus 1 is minus 1, and similarly you have half minus 0 by minus half is also equal to minus 1. So you have f of xi minus f of 0 by xi here. This sequence converges to minus 1. This sequence converges to 1, even though both the xi sequences converge to 0. So that means that limit x approaching x star, f of x minus f of x star by x minus x star does not exist, because I chose two sequences converging to x star and I am getting different values for f of x minus f of x star by x minus x star, the limit of that. So this particular function f of x equal to mod x or absolute value of x is not differentiable at x star is equal to 0. Okay. Here are some more further examples for you to work out. Let us say f of x is equal to 4x plus 2 if x is greater than or equal to 2. This is equal to, let us say, 2x plus 8 if x is less than 2. What can you say about this function? Is this function differentiable at x star is equal to 2? First off, you can immediately say that this function is not even continuous at x star is equal to 2. Why is that? Because if you approach f from the left, which is, then you get a limit of 12. If you approach it from the right, you get a limit of 10. So that means that your f is not even continuous at x star is equal to 2, then it means that clearly it is also not differentiable at x star is equal to 2. Another example, example 3, and say f of x is equal to 4x plus 2 if x is greater than or equal to 2, and 2x plus 6 if x is less than 2. This particular function is in fact continuous at x star is equal to 2, but you can show that limit x approaching 2 plus. So by this we mean x is approaching 2 from the positive side, that is, for example 3, 2.5, 2.25. This is an example of a sequence that approaches 2 from the positive side, 2 plus. We have f of x minus f of 2 by x minus 2 is exactly equal to 4. But if you have the x approaching 2 from the negative side, which is limit x approaching 2 minus f of x minus f of 2 by x minus 2 is equal to going to be 2. So you have even though you have two, both the sequences are approaching 2, f of x minus f of 2 by x minus 2 approaches 4 for one sequence and approach is equal to 2 for another sequence. So which means that limit x approaching 2, f of x minus f of 2 by x minus 2 does not exist. So f of this particular function is not differentiable at x star is equal to 2. Okay. So that is a couple of examples done. Right. Let us try to interpret the derivative expression. Right. What is the derivative expression? That is f dash, let us say a function is differentiable. That means that f dash of x is equal to, let us use a different color here, f dash of x is equal to limit dash of x star. F dash of x star is simply the limit x approaching x star f of x minus f of x star by x minus x star. Or in other words, this would be another expression that you might see somewhere else, which is f dash of x star is equal to limit h approaching 0 f of x star plus h minus f of x star by h. This is an alternative expression that you might see for the derivative, which is exactly the same as the first. These two expressions are exactly the same, but the second expression is easier to interpret. Right? This limit h approaching 0. For example, let us give an example of a sequence that approaches 0. Let us pick, let us say 1, half, 1 by 4 and so on. If you do that for h equal to 1, Let us say we pick x star equal to this point, x star comma f of x star is this point. We can pick let us say h equal to 1, this is 1, this is x star plus 1 comma f of x star, and this point is simply x star plus 1 comma f of x star plus 1. So, you can imagine a triangle with these 3 points, just x star comma f of x star plus 1 comma f of x star plus 1 and x star plus 1 comma f of x star. You can imagine the triangle like this, and this side, the length of this side is exactly equal to f of x star plus 1 minus f of x star. The length of this side is exactly equal to 1, and this ratio corresponds to f of x star plus h minus f of x star by h. You can reduce h even further from 1 to, let us say you can reduce it to half, right, in which case it becomes x star plus half comma f of x star plus half, x star comma f of x star, and this point would be x star plus half comma f of x star. So, the length of this line segment is going to be f of x star plus half minus f of x star, and the length of this line segment is going to be equal to half, and this is the ratio of these two corresponds to f of x star plus h minus f of x star by h, and you can keep on reducing this line segment h from 1 half 1 by 4 and go all the way to 0. If you do that, you end up with the ratio of two terms which exactly corresponds to the derivative. This blue line here, when h is equal to 1, you can see there is a gap between the blue line and the black curve corresponding to the function, and that gap is lesser when h is equal to half. There is still a gap here, you could zoom in and see that there is a difference between the blue line and the black curve, but it is much lesser now, and you can keep on reducing h, and if you keep on reducing h to a point where h is practically 0, you would get the line joining x star comma f of x star and x star plus h comma f of x star plus h. You extend it, you get this red line, and the slope of this line, which is simply the ratio of this line, this length and this length, is exactly equal to the derivative, which is f dash of x star. So, this is another interpretation that you might see for derivatives, which is a standard interpretation. That is, the slope of a function at a point is simply given by f dash of x star. So, what do you mean by slope of a function? Well, you just construct a linear straight line which approximates the function. We will come to the approximation viewpoint soon enough, but this is another standard usage of derivative that you will find it used often in literature. Okay. Yeah. So, with that we can wrap up this module and move to the next module, where we link derivatives to linear approximations in a more formal way. Thanks.